Hello, yeah, thank you. So, so let's just wait for 2 more minutes, hoping for more participants to join, and then we can start today's discussion. One more minute, and then we will start today's discussion. Okay, so let's start today's discussion. So let me just reiterate. As per our like our previous weeks, we will just give me 1 second. Yeah. Similar to our previous week's sessions, we will try to briefly look into the concepts that were discussed by Professor Anand in the lectures. Of course, uh, I will just try to briefly go through them just for your revision, and if there is any discussion required, if at all, we will try to do that. But if there's any pertinent doubt, even after discussion, I would encourage all of you to put that doubt in the discussion forum of this particular course. We look into it and respond that afterwards accordingly. Okay. And once again, I will just say that all the required information or required clarifications are well versed, or I would say well contained within the lectures and the suggested textbooks, so you can refer to that as well afterwards. But this session we will just try to focus more upon solving some problems, similar types of problems that are relevant to your assignments as well as your examination. Okay, so after discussing the topics that were taken by Professor Anand in the lectures, we will directly.
Sir, excuse me.
Yes, please.
Sir, एग्जाम में हमें एमसीक्यू आएगी या थियरी भी आएगी?
Okay, so it will be a mix of both of them, similar to your assignment. It will be a mix of both of them.
Marks, how much?
Marks, I'm sorry, I do not have an idea about that. So, okay, thanks for asking. Okay, so if required, I will just try to look into it and maybe answer it to you in the next lecture. But right now, I do not know, so I'm sorry for that. Okay. Okay then. So yeah, as I was saying, I will briefly go through the topics by Professor Anand, and then we will try to solve some problems. And yeah, that's the agenda for today's discussion. Okay. So with that, let's start today's discussion. So, if you recall, uh, in the beginning of this course, we mentioned that thermodynamics is a very vast subject which primarily deals with the energy and its conversion and its transformation. Okay, and we discussed about these modes of energy transfer, that was heat and work. So by now you might have got an idea about heat and work interactions as well as about internal energy. So uh, by having attended the past two lectures and sessions, you by now you should have gotten a bit idea of what heat and energy are, or heat and work are. Okay, but as mentioned by Professor Anand, it is some kind of an chicken and egg thing. So we mention heat in terms of work, then work in terms of heat, and specifically internal energy in terms of both of them. So they are interconnected in a way, and this relation between heat, work, energy, and their conservation is given by the first law of thermodynamics, okay, and which is the primary topic of discussion for today's session, okay. And by now, briefly at least, I might have, as well as Professor Anand in his lectures, would have introduced you about the first law of thermodynamics, that is the law of energy conservation. Okay, so this will be the primary point of discussion for our today's discussion, as well as the problems that are depending on this topic. Okay, and so we till now we have discussed about work interaction, work interaction, interactions, and internal energy, right? And internal energy, we have discussed about it in the previous classes, and we have not, and we have also mentioned about this heat transfer, it is Q, but we have not dived deep into it. Okay, so before officially introducing the first law of thermodynamics, I think it is just wise for us to briefly discuss about heat. Okay, so heat, I think by all means you all are quite aware of that, but in terms of thermodynamics, it is similar to work. Okay, it is a boundary interaction between a system and the surrounding, which occurs solely by the virtue of the temperature difference. Okay. Yes. So for heat transfer to occur, there has to be a temperature gradient between the system and the surrounding, and vice versa. Okay, so that's the primary requirement for heat transfer to occur. And moreover, this spontaneous heat transfer, that is the heat transfer that takes place by itself, occurs between the system and the surrounding at different temperatures, and the direction of this heat transfer is always from higher temperature to lower temperature. Okay, so the thing is that heat transfer from higher temperature to lower temperature is only, or I want to say only, is observed in spontaneous heat transfer. Okay, or the heat transfer that occurs by itself. Okay, so for example, I will again go back to the example that I took in the very first session, that is a hot cup of tea. Okay, so given that your surrounding temperature is around room temperature, say around 300 Kelvin, or I must say 25 degrees Celsius, around that point, and your T is around say 80 degrees Celsius. Okay, so it's just it would just make sense that the hot tea that is kept in a room temperature surrounding would cool down after some time. Okay, because of the heat transfer from the tea to the surrounding. Okay, but it's not always the case. You might ask, sir, isn't it possible that I heat the tea up even more? Yes, of course you can do that. It's 80 degrees Celsius initially right now. Now, if you put the tea in a induction, then the temperature of the tea will go up, right? Which is basically where the heat transfer is occurring from, where you're heating up the tea using an external energy source, given that your tea was interacting with a much colder surrounding. Okay, so here you can see that this kind of heat interaction is not a spontaneous heat interaction, but rather a non-spontaneous heat interaction where you are using external agencies to reverse the direction of heat transfer. Okay, or in this case, what's happening is that you are using an energy source to heat up the tea, but I think you get an idea right now that this kind of energy interaction can occur. But a more specific example would be your air conditioner. Okay, for example, in summers, right? In summer, right now, if in most of the part of our country, the temperature is quite higher than the room temperature, it's around 30 degrees Celsius, 35 degrees Celsius, right? So initially, after the night, the room cools down because of the temperature at the night. But as the day goes by, the temperature of the room rises up because of the rise of the temperature in the surrounding, the outside the room. Right, heat transfer occurs from the outside towards our home, which increases the temperature inside our room. But we have another source with ourselves, that is the air conditioner, that can help to cool down our room. Okay, now you mentioned how it is happening, like how we are able to cool the room temperature by using these external agencies. Okay, so this is basically what non-spontaneous heat transfer means, that we are using the energy from the outside our room to cool down the temperature within our room. Okay, so that's generating a non-spontaneous heat transfer. So heat transfer is occurring from a higher source to a higher temperature source to a lower temperature region. So that's what I meant. So heat transfer can occur in both directions, from hot to cold and from cold to hot, but the spontaneous direction of heat transfer is always from hot to cold, from higher temperature to lower temperature. Okay, and this direction of heat transfer or direction of energy interaction, the directional component of heat interaction and energy interactions would become more relevant when we discuss about entropy. Okay, one of the most important uh, topics in this course. Okay, so once we look into it, basically when we will introduce the second law of thermodynamics, we will get more idea like about the directionality of the heat transfer. So right now, for the first law, we are just concerned in the balance of your energy interactions, that balance between the heat interaction, work interaction, and the energy and the internal energy. Okay, so I hope this is clear. Let's proceed further. Yeah. So similar to work interaction, heat transfer or heat interaction is a path function, and it is occurrence, not a property of the system, and thus is dependent on the path followed by the system to attain it, okay, or to attain or reject heat in the system. Okay, it is dependent on the path followed by the system. So the path followed by the system would basically mean the type of process that was incurred for the heat interaction to occur. Okay, so you can see that in this diagram, say the system follows two different paths, say path A and path B. Okay, for some energy interaction, for some heat transfer to occur. Okay, so since this heat transfer is a path function, heat transfer from 1 to 2 through path A will not be equal to heat transfer from 1 to 2 through path B. Okay, so this will not be equal since it is a path function, but energy interaction would remain same because it is a state function. Okay, we'll look into that one example. Yeah, and the unit of this heat interaction is same as energy and work done, that is joule or calorie. Okay, so for our course we will primarily focus on joule, this is the SI unit, but calorie is also one of the units to quantify heat, work, and energy interactions. Okay, yeah. The other important parameter is the sign convention. So previously we discussed about the sign convention for work interaction. So similar to that, we need to follow a standard sign convention system, sign convention for heat interaction as well. So in this case, we have when the heat is transferred into the system, it is taken as positive, and then when the heat is transferred out of the system, it is taken as negative. Okay. So if you recall, in the case of work interaction, work done by the system was taken as positive, and work done on the system was taken as negative. Okay, so it's just a good practice to remember the sign conventions. Of course, by practice or by regular solving of some thermodynamic problems, you will be quite relevant, you will become quite relevant to it, but still it's a good practice to just remember it. Okay, so now let's come into the first, just discuss the zeroth law of thermodynamics. So the zeroth law of thermodynamics states that if a system A is in equilibrium with system C, and if a system B is in equilibrium with system C, then A and B must be in equilibrium with each other. Okay, and this zeroth law of thermodynamics is the basis of the principle of thermometry. That is how the basis of the design of the thermometers that we use to measure temperatures. Okay, the details of that I won't go. I think Professor Anand have taken ample amount of time to discuss that, so I will just go through briefly through them, and there are some problems, two problems I guess we have for today's discussion. I think that would be wise that if we look into them, emphasize on them more rather than the theory part, because it was already discussed in the class. Okay, so I will try to just go through them quickly, and yeah, we'll emphasize more on the problem. Okay, so there was a discussion on the liquid in glass thermometer. The one example was taken, and then where is the way of quantifying temperature was based on the expressing the length, the column length as a suitable function of temperature. Okay, where we assume that the temperature and the length of the liquid in the thermometer will have a linear relationship given by L is equal to A plus BT, where A and B has to be empirically evaluated. Okay, And usually, as mentioned by Professor Anand, for the purpose of calibration, that is finding the value of A and B, these constants are usually found out using the well-known temperature values. Okay, for example, if the liquid, say I'm just saying, if the liquid inside the thermometer is water, okay, for example, you're using water to quantify the temperature, then it is well known that the water will freeze at a temperature of 0 degrees Celsius and would boil at a temperature of 100 degrees Celsius. So if you substitute the value of these two things here, then you can easily find the value of A and B. Then your thermometer will be well calibrated. Okay. Similarly, like if you're using, say, different types of liquids, if you know the boiling and melting points, then you will be able to calibrate. Given that your temperature and the length of the length in the length of the liquid in the thermometer has a linear relationship. Okay, so that's also a suitable uh, requirement for the types of liquid that are chosen for thermometers. Okay, yeah. Then there was ideal gas thermometers. I think I will skip this part. Okay. Similarly, like there are two modes: constant volume mode and constant pressure mode. So in constant volume mode, volume remains constant and the pressure varies linearly with temperature. Inversely, in the case of constant pressure mode, pressure remains constant and volume varies linearly with temperature. Okay. So these are two things. I will just go through it quickly. Yeah. Then there are thermoelectric based devices, thermocouples, something like that, uh, where there is a relationship obtained between the temperature and the potential difference. And again, they assume that the electromotive force has a relationship given by A plus B T plus C square, where again A, B, C are constants, and you need to use some empirical methods to find the value of this constant and then calibrate your thermometer to make it suitable for measuring temperatures. Okay, so the details of that, I think I won't go. There are some problems that we can look into. That will be more helpful for for all of you. So I'll just try to stick to that. But again, if there's any doubt or specific, I would say, inquiry that you want to do regarding these kind of things, you can always put them in the discussion forum. We'll look into it and we'll answer back. Okay. But for the sake of this session, I think let's try to focus on the problems. Okay. There are quite a lot of problems today, so I think it will just be better if we look into that. Yeah. So now I hope I'm moving at a steady pace and it is understandable right now till now. As a yes or no? Yes.
Yes, sir.
Okay. Thank you so much. Who was it? Okay, never mind. But thank you.
Sir.
Okay. Thank you so much. Yeah. So let's proceed further. Yeah. Then comes the different modes of heat transfer. Okay. So let me again just I don't think I need to say it, but out of curiosity or out of interest, I'm just speaking up that these modes of heat transfer or heat transfer in general is actually treated as a separate subject in the, I would say, in the branch of mechanical engineering, because thermodynamics is specifically, or classical thermodynamics, as I must say, is a fundamental part or integral part of the mechanical engineering course of any undergraduate or postgraduate studies. And in their course structure, this thermodynamics and heat transfer are taken as two different subjects. Okay, so this heat transfer or modes of heat transfer are generally taken as separate subject and are quite vast and extensive by themselves. Okay, so here we will just briefly introduce to you about these three major modes of heat transfer, or I would say the three modes of heat transfer that are conduction, convection, and radiation. Of course, these are all mentioned in your lecture notes and was taken by Professor Anand. But if you have not been introduced to heat transfer yet, or you are taking heat transfer course right now, or already have taken it, but just as an idea to you, I will just say that this is a separate course in itself and it's quite vast and extensive, and there are ample amount of problems that might be given from these modes of heat transfer itself. So you can look into it if required, but for the from the perspective of thermodynamics and from the perspective of this course, we will be primarily concerned in the thermodynamic perspective, that is the different laws of thermodynamics, the rate of change of energy within the system, or rate of change of heat transfer. These kind of things we will be more concerned upon. But again, this knowing these different modes, how they are quantified, what are their origin, it is I would say quite interesting to know about. Okay, but nevertheless, I will just stick to what was discussed in the class. I think that would be quite more than enough for this course. Okay, so as mentioned by Professor Anand, there are three modes of heat transfer. Okay, conduction, convection, and radiation. Okay, so we'll look into all three of them separately. Okay, starting with conduction, the thing that becomes quite, that easily becomes relevant to us. In this case, the energy transfer occurs between the molecules, and the law that governs this conduction is given by the Fourier's law of heat conduction, that is given by this relation. Okay, the rate of heat transfer is given by minus Ka times the dt by dx, where dt by dx is the temperature gradient between the two surfaces. Okay, where the heat conduction is occurring. Okay, and K is the thermal conductivity, and A is the area of contact between the two surfaces. Okay, or the surface through which the heat transfer is occurring. Okay, for let's say let's take this example. Consider this is a wall, a cuboidal shaped wall. Okay, then let's consider that we are considering the rate of heat transfer across these two surfaces. Okay, surface 1 and surface 2. Okay, across these two surfaces, then the area of conduction would be this entire area. Okay, okay, then you want to know how much heat transfer or rate of heat transfer between in this area, in this region. Okay, so this will be the area of concern. Then the temperature gradient is basically given by the temperature difference between these two surfaces and divided by the length or the thickness of this particular wall in this case. Okay, depending upon the geometry, your all these parameters will modify, and also the Fourier's law of heat conduction also get modified, because this is for a Cartesian coordinate system. Accordingly, depending upon your coordinate system, say if it is a spherical geometry or a cylindrical geometry, your this Fourier's law of heat conduction would vary. Okay, but nevertheless, for simple cases or cases that we will be dealing with in our course or today's assignments, this simple law would suffice. Okay, the Fourier's law of heat conduction. So the unit of heat transfer is rate of heat transfer is given by watt. Okay, basically joule per second, that is equal to watt. Okay. The unknown term that I think that you might be quite interested upon is this value of thermal conductivity. Okay, so again generally speaking, this Fourier's law of heat conduction is again derived from the Biot-Savart's law for I won't say Biot-Savart's law, it's obtained from the Fourier's law of heat conduction. Okay, it's a entire equation that deals with that quantifies the total energy transfer between a surface. So and that equation is again modified depending upon the choice of your geometry. Okay, so there's that, and there, depending upon the type of system, whether this is isotropic or having uniform thermal conductivity, the the dependence of K with respect to your area. For example, it might happen that in some cases the value of thermal conductivity may change from 0.1 to 0.2. Okay, along this surface also the value of thermal conductivity may change. Okay, so depending upon that, the independence of thermal conductivity from the spatial coordinates or even the temporal coordinates may vary depending upon the problem. But for the most simple cases, this value of thermal conductivity is usually taken as constants. Okay, so that's why Professor Anand has mentioned the range of thermal conductivity for different kinds of objects. Okay, for example, for metals, they will have the highest value of thermal conductivity. So their thermal conductivity values are usually varying around 100. Okay, 100 or greater than that, or usually in that order. Okay, so the unit of thermal conductivity K is given by watt per meter Kelvin. Okay, I won't say K, it's actually kappa, but I'm not able to distinguish it, but it's actually kappa. Okay, so it's kappa. Okay, so the value of this K, or thermal conductivity, then for non-metallic solids is around 1 to 10 watt per meter Kelvin. Okay, then for liquids is around 0.1 to 10 watt per meter Kelvin. Again, for insulators is 0.1 watt per meter Kelvin, and for gases it's around 0.1 to 0.01. So there is a trend that you can observe. The thing is that for thermal conduction to occur, as you can see, as you can know, that it's generally thermal conduction generally occurs because of the vibration of lattices, because of the change in the internal energy of the system, because of the application of heat. So more closer the these lattices are in the system, higher would be the rate of heat conduction. So you can see that as the as the density of the object reduces, the thermal conductivity also reduces. There is a trend that you can observe. Okay. I'm sorry. Yeah. So I hope it was clear. And then we come into the concept of convective heat transfer. Thanks, Prithvi. Thanks. So then comes the concept of convective heat transfer. Okay. So just as a precursor, I will tell you that if thermal laws of your thermal conduction, they have a very analytical equation. As I mentioned, there's a Biot-Fourier law of heat conduction. There is a analytical governing equation that governs the heat conduction. Okay, there's a very nice analytical way, or I would say governing equations that govern the heat conduction in objects. But for convective heat transfer, there is a general trend that this kind of heat transfer is generally empirically quantified. Okay, because if you recall, recall discussion by Professor Anand in the lectures, for convective heat transfer, there has to be a bulk motion of fluid. Okay, and it is only relevant in the case of fluids. It is for gases or liquids. Okay, and in that case, for the convection to occur, or convective heat transfer to occur, there has to be a bulk motion of this liquid, so of this fluid. Okay, either of gas or liquid. Okay, and this kind of heat transfer is usually quantified using empirical formulas. So once, if you are introduced to heat transfer, say say in your next semester, or if you're already reading heat transfer as a subject in your undergraduate or postgraduate even, you will see that this convective mode of heat transfer is usually empirically quantified. Okay, there are different values of some coefficients that are mentioned to quantify this mode of heat transfer. Okay, I think it might become a bit irrelevant right now, but I'm just giving you a brief introduction about it. Okay, so consider a case, very simple case again, that there is a flat plate, okay, which has a surface area of A and a surface temperature of Ts. Okay, and there is a flow of fluid over this flat plate which has a temperature of T infinity. Okay, and because there is a bulk flow of air across or above this particular plate, there will be a heat transfer from this plate to this bulk motion of fluid. Okay, so because of this bulk motion, there will be a temperature gradient between the surface of the plate and the region where we want to obtain temperature. Okay, we want to see the temperature, and that, since there's a bulk flow of liquid, there will be a convective mode of heat transfer. Okay, so, and this convective mode of heat transfer is quantified by this relation that is given by the rate of heat transfer Q dot is given by HA times delta T, where H is the convective heat transfer coefficient. Okay, this is watt per meter square Kelvin. So as I was mentioning, the empirical nature of this mode of heat transfer, or empirical nature of quantifying this mode of heat transfer usually comes handy when evaluating the value of this h. Okay, you will see that this value of h depends on different kind of non-dimensional numbers such as Nusselt number and Prandtl number. Like Nusselt number and Prandtl number. Okay, these are something new to you, but I'm just saying. So they will become quite relevant to evaluate the value of h, and that h will be used to quantify your mode of heat, your convective rate of convective heat transfer. Okay. And just one more thing to add. Say if someone is saying there is a convective mode of heat transfer occurring, one thing to note is that if there is a convective mode of heat transfer, it is sure that there has to be a conduction. Okay. For example, just having giving you an example. For example, there is a flow of liquid above this surface. Okay, above this surface, that is causing convection to occur. Okay, and this plate was heated up to a temperature of Ts. Okay, but the the molecules of this fluid attached to the surface of the plate are not moving because of no-slip boundary condition. If you are introduced to fluid mechanics, I'm just adding on, but the non-moving fluid particles on the surface of the plate and the plate will have heat transfer, and this heat transfer is because of conduction. Okay, so if there is a convection occurring, we need to note that in the case of convection there is both conduction as well as convection. Okay, convection cannot occur without conduction. Okay, so that's one thing to note. It may come as a one mark question, might come, but it's an important fact to know. Okay, again, there are two different types of convection. There is natural convection and forced convection. I think again this was discussed thoroughly, but I will just say in the natural convection, this natural convection occurs because of density gradient. Okay, that is the flow of this fluid above the surface may occur because of density gradient. Like for example, it is kept stationary and it is being continuously heated. Okay, because of heat, the layer of fluid near the surface of the plate will get heated up and will become of lesser density. Okay, and since it is of lower density, then this low density fluid will try to go up and the higher density fluid will try to come down. Okay, and again when the higher density of fluid comes down, it will again get heated up. Again it will become lower density than the upper layer. Again it will try to go up. So this type of motion will continue to occur, and which is popularly known as convection loss. Okay, and as you can see that here there is no external agency that is being used to generate the bulk flow of the fluid, and this motion of fluid or a bulk flow of fluid is only occurring because of the density gradient. Okay, so these kind of flows are known as natural convection, and you can see that the value of this H generally for gases in the case of natural convection is from 5 to 25 watt per meter square Kelvin. Okay, similarly in the case of liquids it is higher, it's around 5 to 1000 watt per meter square Kelvin. But in the case of forced convection, for example, rather than the density gradient generating the bulk flow, say I am using an external fan. Okay, I am using a fan to flow the liquid or force the liquid to flow through the plate. Okay, in that case, see, I am using an external agency to force the flow of liquid over the plate. So this is known as forced convection. Okay, and in this case you will see that even if your geometry is same, the temperature difference is same, but the rate of heat transfer will increase because of the higher value of H in the case of forced convection. So you can see that for the same geometry and temperature difference, the value of H or the convective heat transfer coefficient is higher for forced convection when compared to natural convection. Okay, for gases now it varies from 25 to 50, and for liquids it varies from 50 to 2000. Okay, so the thing is, if you, for example, if you are solving a problem and getting a value of H, okay, given that your problem is based on forced convection and you are getting a value of H for liquids around say 5 to 25, so if that occurs, then you think that it might not be correct, because I know that for liquids, for forced convection cases, the value of H usually varies from 50 to 2000. Usually say from, it should be around 1000, at least greater than that. Okay, so it's just a good way. If you know the range of these values, you will know that your answer might be faulty. Okay, if you know the common values of this H for different types of flows. Okay. Then for boiling phase change, the value of H is usually around 2500 to 10,000. Okay, I will look into it once it becomes more relevant. Now for radiation, this is again a transmission energy through electromagnetic waves in space. Okay, then the formula that governs uh, the rate of heat transfer through radiation is given by the Stefan Boltzmann law, and is given q dot is equal to epsilon times sigma a Ts to the power 4, where Ts is the surface temperature of your object, okay, which is emitting your heat. Okay, and then sigma is the Stefan-Boltzmann constant given by 5.67 into 10 to the minus 8 watt per meter square Kelvin to the power 4, and epsilon is the emissivity of the surface compared to a black body. Okay, so, and this value of emissivity is again given for different kinds of surfaces. Okay, yeah. So again a brief introduction. For in the case of work transfer, we saw that in the case of work transfer, we were, I hope this is visible on the screen. Yeah. In the case of work transfer, we used PV plot to to get a quantitative idea of how work transfer is observed, okay, or quantified, and we saw that the area under the PDV curve gives us the value of work transfer. So similar to that, in the case of heat transfer, there is a different plot. This is the temperature entropy plot, okay, and the area under this TDS plot or temperature entropy plot gives us the net value of heat transfer. Okay, it's something that will become quite relevant when we discuss about different thermodynamic cycles. It will become quite relevant at that point, but still a good way to introduce it to you. Okay, yeah. So now let's formally introduce you to the first law of thermodynamics. Okay, so we already I briefly mentioned in the last class through a numerical problem that we saw that if there was a thermodynamic cycle, I don't recall the shape of the thermodynamic cycle, uh, just say there's thermodynamic cycle occurring. In that case, we found that the summation of the total heat interactions in the system and the summation of total work interaction of the systems are equal in the case of a cyclic process. Okay, so in general, the first law of thermodynamics is given by this law, that is, say for example, if a system is going from state 1 to state 2, then the total heat transfer is equal to the change in internal energy plus the total work transfer. Okay, and the sign of this work transfer again depends on whether the work is done on the system or work is done by the system. Similarly, the sign convention for your heat interaction depends on whether heat is transferred into the system or heat is rejected by the system. Okay, so this is the general law or the general form of the first law of thermodynamics. Okay, but things become interesting when the thermodynamic process occurring in the form of a cycle. In the case of a thermodynamic cycle, the total heat interaction would be equal to total work interaction. Okay, so given by this relation. Okay, so now there is a elegant, I would say, proof or way to show that our internal energy or the energy of the system is indeed a point function. Okay, so let us look into it. Consider a thermodynamic cycle, okay, occurring from point 1 to point 2. Okay, so it might happen that we can follow part A to go from we can follow part A to go from point 1 to point 2, then come back to point 1 following part B. Okay, it may happen like that, or we can go from point 1 to point 2 to part C and then come back to point 1 to part B. Okay, so you can see that the way we go to point 2 varies depending on the part followed, either by A or C, but the way we come back to point 1 is through B only. Okay, just one second. Okay, so for example, these different parts would imply different types of processes that were followed to obtain the change of state. For example, it may happen that point 1 may part A might be an adiabatic mode of heat transfer. Sorry, I'm not so adiabatic. Might be an isothermal heat transfer. Okay, point C might be a polytropic process with an index value of say 1.3. Okay, but point B is a isobaric process where the heat transfer is occurring in a constant pressure way. Okay, so there might be different ways through which the change in state has been obtained. Okay. Now from the first law of thermodynamics, since this is occurring in a cycle, we get that summation of the net work interaction is equal to summation of net heat interaction. Okay. Say I am considering the first part, that is 1A2 B1. Okay. 1A2 B1, this part. Okay. Then work done from 1 to 2, summation of all work done, work done from 1 to 2 through A, then plus work done from 2 to 1 to B would be equal to the net heat transfer from 1 to 2 through B and the net so it is A actually, okay, it's A. Net work done from 1 to 2 through A plus net heat interaction from 1 to 2 through A, then net heat interaction from 2 to 1 through B. Okay, if you rearrange this, just take, for example, just take this one here and take this one here, you will get that Q1 to 2A minus W1 to 2A is equal to minus of Q2 to 1B minus W2 to 1B. Okay, so that is equation 2. Similarly, now if we follow a path, say 1C2B1, okay, 1C2B1, then again it comprises a thermodynamic cycle. Okay, so we have summation of net heat interaction is equal to summation of net work interaction, then W1 to 2C plus W2 to 1B is equal to W1 to 2 Q1 to 2C plus Q2 to 1B. Again, rearrange this, you will get that Q1 to 2C minus W1 to 2C is equal to minus Q2 to 1B minus W2 to 1B. Now, if you compare these two equations, that is 2 and 3, you will see that the right hand side of your equation is the same, is exactly the same. Okay. So, it implies that this it will imply that Q1 to 2A minus W1 to 2A is equal to Q1 to 2C minus W1 to 2B. Okay, so even if your net heat transfer or the net work transfer is dependent on your path, but this entity, that is heat minus work, is independent of your path. You can see that Q1 to 2A minus Q1 to 2 minus W1 to 2A is equal to Q1 to 2 minus W1 to 2C. Okay, so you can see that this difference between heat and work is a path independent property. Okay, so if it is a path independent entity, I should say right now, if it becomes a path independent entity, then this becomes a property of the system because it is path independent. Okay, and this difference from the first of thermodynamics is your energy of the system. Okay, so this proof shows us that the energy of the system is an independent of path and is thus a property of the system. Okay, or a point function. Okay, this is a point function. Okay, or a state function. I hope this is clear. This discussion was clear. Okay. Yeah. Okay then. So again, there is a following that is a brief discussion on different kinds of energy of the system. So Professor Anand showed that the energy of the system might be comprised, or the total. Just one second. Just 1 second. I don't understand the last two steps. Okay, let me just highlight it. You can just say yes or no. Okay. Do you mean these two steps, like these steps? Yes. Okay. Okay. Fine. So if you're having confusion in the last two steps, it means that you are quite okay with equation 2 and equation 3. Okay, so if you're okay with that, let us proceed after that. Okay, so from 2 and 3, let me just write it again. From 2 and 3, you can see that your right hand side of the equation is exactly the same. Okay, from 2 and 3, the right hand side of your equation is exactly the same. Okay, that's one thing to note. Okay, so if that's the case, it will imply that your left hand side are equal to each other. Okay, so Q122A minus W122A should be equal to Q122C minus W122C. Is it fine? From equation 2 and 3. If the right hand side is same, exactly the same, then then left hand side should be equal. Yeah. So I can say that Q122 minus W122 through path A should be equal to Q122 minus W122 through path C. Okay, so I'm saying that even if Q122A is not equal to Q122C, okay, and W122A is not equal to W122C, okay, because these are path functions, but their difference, the difference between Q122A and W122A is equal to Q122C and W122C. Okay, even if these are dependent on path, but their difference through different paths are the same. Okay, so that's what I wanted to show, or that is being showed by Professor Anand in the steps. So this difference is same for any path or independent of path. Okay, so from first law it will basically imply E2 minus E1 for path A is equal to E2 minus E1 for path C, from the first law, from this relation. Okay, so it implies that this change in the internal energy is independent of the path, even if individually Q, W are path functions, but the difference is a point function or a state function. So is it clear? Okay, thanks Jay. Astha, is it clear? Yeah, thank you Astha. Okay, thank you. Okay, yes. So as I was saying, now following that, Professor Anand has discussed about different types of energy of the system that comprises the total energy of the system, that is E. Okay, that's E here. E here is actually the total energy of the system, which is can be comprised of can majorly be comprised of the kinetic energy, potential energy, and the internal energy. Okay, so sir showed that again different ways through which you can quantify your kinetic energy and potential energy. So kinetic energy can be quantified as mv square by 2. You can go through the steps in the lectures. I will not go through it right now. Potential energy is quantified by mgh, and your internal energy is, again, for ideal gases it's usually quantified by cv delta t or cp delta t, depending upon how the process is achieved. Okay, but you look into it once we get to some relevant examples. Okay, so for example, in this case, if there is a piston cylinder type of system where you are supplying, and this is your control volume. Okay, so for example, if you are I will say your control volume. Okay, with variable size. Okay, deformable control volume. Okay, one way to say it. Now if you are saying that you are applying a heat of 100 joules into the system, which is resulting in this gas to expand, and because of the expansion of the gas within the cylinder, it is able to push the system outwards to obtain a certain amount of displacement, which is resulting in a net work done against the atmospheric pressure to be equal to 50 joules. Okay, then the total internal energy stored within the system would be 50 joules from the first law of thermodynamics. Okay, the net heat interaction is positive because heat is applied into the system, so it is 100 joules, and work is done by the system. I should write it in the initial stage. It is Q1 to 2 would be equal to delta E plus W1 to 2. Okay, so heat is applied into the system, so it is positive. Delta E is delta E. Work is done by the system, since it's expanding against the atmospheric pressure, then it is positive 50. So delta E becomes 100 minus 50 is equal to 50 joules. But how it is delta U? The thing is that now you need to think. Okay, we know that E is Ke plus Pe plus U. So you can see that in this particular example, there is no major change, no major significant change in the kinetic energy or the potential energy. Okay, so the type of energy that has major contribution to the total energy system is your internal energy. Okay, so with that approximation or that justification, we can write that delta E should be equal to delta U. So just give me 1 second. Delta U should be equal to 50 joules. Okay. So depending on the type of the system, the contribution to the total energy would vary. But from again, I will say that from thermodynamics perspective, or the types of problem that we will deal with in majorly, would emphasize more on the internal energy of the system, that is delta U. Okay, so that's what I wanted to mention. Then again, there is the introduction of enthalpy, where it is thermodynamically defined as the sum of your internal energy U plus the product of pressure and volume. Okay, or if you divide it by mass, it will become the specific enthalpy. H will be equal to small u plus pressure times specific volume. Okay, V. So it's just a thermodynamically defined entity or property of the system, where specific enthalpy becomes a property of the system. Okay, because it's a specific property, and this thermodynamic property becomes more relevant in the case of flow systems. Okay, we will see if we come to this some kind of example that has flow through the system. You will be able to appreciate the introduction of this enthalpy. Okay, so there's that. Now let us look into some problems. Okay, so again, these problems I will just go through them once, just briefly, because this was taken by Professor Anand in the lectures. Okay, so I'll just go through it once. Maybe after this, let me just see. Okay, there are, so I think there are 2 problems. So yeah, I think I have time to go through both of them. Then we can directly start the problem solving part. Okay, where I will give you questions. I will give you a certain amount of time. You will have to solve them. If you have doubt, you can ask. Then we can try to show the solution to everyone. Okay, so that's the general practice. Let us go through it. Go through this example very quickly. This is already taken in the class, in the lectures, but I'll just go through it very quickly, so that you can just brush up your solving skills, and then we can go to the real thing. Okay, so the tangential force acting on a cutting tool of a lathe when turning on a metallic workpiece of 80 mm diameter is 180 Newton. Okay, so it is the the cutting tool is exerting a force of 180 Newton on the workpiece. Okay, after 8 minutes of turning, the internal energy of the workpiece and the chips is increased by 80 kilojoules. Okay, so after turning it for 8 minutes, turning the workpiece for 8 minutes, the internal energy of the workpiece and the chips that is coming out of the workpiece because of the turning has increased by 80 kilojoules. Okay, if the frequency of the revolution of the revolution of the workpiece is 250 revolutions per minute, estimate the heat transfer from the workpiece and chips in this time. Okay, so if you look into it, all the specifications are already given. The net change in the internal energy has increased from 8 to 80 kilojoules. Okay, and the work is done on the system. Work is done on the workpiece through the tool, and since it is having a rotational motion, this kind of work done can be quantified through your net uh, moment applied on the tool. Okay, so the net moment, that would be force times your the perpendicular distance. So T would be F times R, that is F, the normal force was 180 Newton as mentioned in the question, and the radius is 80 divided by 2 or 40 millimeter. Okay, so the net moment or torque in this case is 7.2 Newton meter. Okay, now the revolution per minute is 250, so the revolution per second you have to find to quantify the net work done. So N will be 250 divided by 60 or 4.167 rounds per second. So we know that the net work interaction is given by torque times the angular displacement. Okay, so the angular displacement is given by 2 pi nt, where n is in rounds per second. Okay, and t is the total time. So this will become 2 times pi times 4.167 times 7.2, that is the net torque, and t is 480 seconds, 8 minutes. Okay, so if you do that, you will get work done as 90.4 kilojoules, and it is minus because work is done on the system, where your system is your workpiece. Okay, so work is done on the piece through your tool. Okay, cutting tool. So now first of thermodynamics, we have that Q1 to 2 is delta U plus W1 to 2. Okay, then delta U is 80 has increased. Okay, they mentioned that internal energy has increased to 80 kilojoules. Okay, so it is 80 work is done on the system by this cutting tool, so it is minus 90.4. Okay, so the net heat transfer is minus 10.4 kilojoules. Okay, so heat is being dissipated out of the system. So that's what we get from this thermodynamic law. Okay, again, it's a very simplified portrayal of the real problem, but it's just a way to introduce you how to apply the first law of thermodynamics. Okay, the second problem is now based on your principle of thermometry. So as mentioned in the question, it is mentioned that there is a linear relationship between your two temperature scales. Okay, where say it is TA and TB. Okay, in the I will not say linear, it's a quadratic relation actually. It's actually so it has a to the power 2 dependence. So TA and TB has a quadratic relation given by TA is equal to K plus LTB plus MTB square. Okay, so it is given that for TA is equal to 41 degrees Celsius, for TB is equal to 30 degrees Celsius. Okay, so you can treat this something like I can say two different temperature scales. Okay, you have two different temperature scales where temperatures of the corresponding scales are given as are having indices of TA and TB. Okay, so we say for example we need to have a calibration between these two different temperature scales. Okay, which tells us that for TB, when we measure a temperature of 30 degrees Celsius in the first thermometer, say TB, we get at a corresponding value of TA as 41 degrees Celsius. Okay, so the question is you need to find the value of TA for TB is equal to 41 degrees Celsius. Okay, and the fluid that is being used in both these temperature scales are water. Okay, so that's one thing. Okay, and these two thermometers are calibrated at the steam points. So it means that this TA and both TA and TB would be equal to 0 at the ice point and would be equal to 100 at the steam point. Okay, that's what it means that they're calibrated. The thermometers are calibrated at the ice and steam points. Okay, you just need to tell us, like, given these three relations, you need to find the value of TA for TB equal to 41 degrees Celsius. I hope the question is clear. Okay, so the main thing to look is the consistency of your problem, whether it is consistent or inconsistent. So you can see that there is a quadratic relation between TA and TB. Okay, and there are three constants basically, K, L and M. Okay, so you know that for the problem to be consistent, you need to have three equations for your three unknowns. Okay, so the three equations can be obtained by the three relations that we have. The first is that for TB equal to 30 degrees Celsius, we have TA equal to 41 degrees Celsius. Okay, so if you substitute the value of TB here, you get one equation. Similarly, since they are calibrated at the ice and the steam points, you again get two different equations, that is TA equal to 0 when TB equal to 0, and TA equal to 100 when TB equal to 100, because they are calibrated at the ice and the steam points. Okay, so if you substitute the value of TB equal to 0 in this equation, you get that TB equal to 0 will imply both these terms are 0 and T is also equal to 0, so K is equal to 0. Okay, so that's the first relation that we get. Similarly, if you substitute the value of TB equal to 100, T will also be equal to 100. So if you substitute that, you will get that 100 is equal to 100L plus 10,000 M. Okay, just substitute the value of TB here. K is 0, so TB square is 100 square or 10,000. TB is 100, so T is again 100. So 100 is equal to 100L plus 10,000, 100L plus 10,000 M. Okay, so those are two relations that you get. And finally, if you substitute the value of TB is equal to 30 degrees Celsius, you get T equal to 41. So 41 is equal to, again there here K is already equal to 0. You will have 41 is equal to 30L plus 900 M. Okay, so now if you solve equation 1 and 3, there are two equations and two unknowns, that is L and M. You will get that L is equal to 1.52 and M is equal to minus 5.24 into 10 to the minus 3. I think I should write it as point, so it does not create any confusion. Okay, so with that you have got all the values, and K is equal to 0. We already got here. Okay, K is already equal to 0. Okay, so now if you substitute the value of all these constants K, L and M, you will get that for TB equal to 41 degrees Celsius, you will get TA as 53 degrees Celsius. Okay, so that's what was discussed by Professor Anand. So I think it should be ideally clear, but still if you have any doubt in this question, you can ask me. Otherwise, I will try to directly go to the problem solving part. Okay, so I hope this problem was also clear in the lectures. So can we proceed? Okay, thanks Jitendra. Okay, so now let's directly dive into the problem solving part. Okay, so I hope my screen is visible. Okay. So this is the first question. Okay, let me zoom out a bit. So consider two slabs of equal length, breadth and thickness, made of two different materials having different conductivities K1 or K2, or ideally kappa 1 and kappa 2. Okay, the rates of heat transfer through the slabs in the x direction is shown and are found to be same, that is Q dot. Okay, if all other conditions are the same and the slabs are having temperature T1, T2, T3 and T4 as shown, where T3 is greater than T1, which is greater than T2, which is greater than T4, choose the most appropriate option. Okay, so I hope the question is clear. So there are two different slabs having this exact same dimensions, okay, length, breadth and height, and the heat transfer along the x direction is given as Q dot, which is the same for both the slabs. Okay, if that's the case, and the temperature relation is also given, that is T3 is greater than T1, T3 is greater than T1 and T1 is greater than T2, which is greater than T4. Okay, so this is the temperature relation that is being shown. So if that's the case, find the relationship between the two thermal conductivities. Okay, so the clue is you need to use the Fourier law of heat conduction. Okay, or a much more simplified way would be, say, T2 minus T1 divided by L. Okay, so this is the law that you need to use. Okay, so it is 7:08 now, so I will give you 4 minutes to try it out. It's quite simple. Just it's already told that Q1 is equal to Q2. Okay, So you just need to substitute this relation for these two different slabs, then find the relation between K1 and K2. Okay, I'll give you 4 minutes. Take your time. If you're in doubt, you can ask. Otherwise, we can. I will show you the solution after discussing, and then you can proceed to the next question. K1 greater than K2. Okay. So okay, thanks Jay. Let us wait for others to respond as well, and let's see whether it's correct or not. Okay. 3 more minutes. Let's try it out. So Jay says K1 is better than K2. So let's see if someone says otherwise. Okay. Try it out. It's not that difficult. It's just simple mathematical manipulation. The only thing you need to focus on is the temperature relations. That is T3 greater than T1, greater than T2, greater than T4. So if you're able to quantify them, like understand the relation, then you will easily get the relation between K1 and K2. So you see that A is equal because all dimensions are equal. So A would be cancelled out from both the sides. So the length is also the same. So only thing that will remain are K1, K2, T3, T1, T2 and T4. Find the relationship between T3 and T2, T1, T2 and T3 and T4. You'll get an idea, and then you can easily say how K1 and K2 are related. Okay. Or I would say specifically the difference between, yes, Asta also says K1 is greater than K2. So I think more or less everybody would have. Okay, 1 more minute is left. Let me just not rush from my end. 1 more minute. I think it's understandable. It's easily understandable. So it's fine. Both Asta and Jay says that it is K1 greater than K2. Let's see if other students also reply. One more minute. I think it is. Okay. So I think I can show it here directly as well. I want to show the solution. So here we will have, and yeah, moreover, yes, both of you are correct. K1 is greater than K2 is the correct answer. Okay. So we have K1. Yeah, using this law, Fourier's law of heat conduction, we have K1, A1. Then it would be T1. Sorry, negative of T2 minus T1 is equal to say x1 is equal to K2 minus K2 A2 T4 minus T3 divided by x2. Now since all the dimensions are the same, so this A1 A2 will get cancelled out, x1 x2 will get cancelled out. So we will have, considering the minus sign, we will have K1 T1 minus T2 is equal to K2 T3 minus T4. Now we will have K1 by K2 is equal to T3 by minus T4, T3 minus T4 divided by T1 minus T2. Okay, just simple rearrangement. So now the thing is, because T3 has the highest value, which is greater than T1, which is greater than T2, and which is greater than T4. So since T3 has the highest value and T4 is the least value, so it just simply implies that, and T1 and T2 are intermediate, so it simply implies that this difference of T3 and T4 has to be greater than this difference between T1 and T2 from this relation. Okay, it's easily understood. So which would imply that K1 numerator is greater than the denominator, so K1 should be greater than K2. Okay, so it was quite simple. Let's see whether, yeah, okay, this question is again interesting. It's a more theoretical, in a more theoretical sense. Okay, so the question is which of the following properties are desirable for thermometric liquids in a liquid in glass thermometer? Okay, and more than one options could be correct. Okay, so I think I can give 2 minutes. I can, of course, you can put in your answers in the chat. Let us just look into it. There can be more than one option that might be correct. Okay, so you can give your answers. Let's look into them, discuss them, and then I think we'll proceed. Okay, 2 minutes, 7:15 to 7:17. Say you can just discuss your answers. Tell your answers, and we'll discuss them. Okay, Astha says B, C, and E, where B is large coefficient of thermal expansion. Jay also says B, C, and E. C is low freezing point, high boiling point, and E is thermal expansion. So the liquid should have linear relationship with temperature and desired range of measurement. Okay, yeah. Okay, so as it seems that all of you are telling the right answer, so since 3 of you have mentioned it, so it is correct. The required I must say required properties are that you should have a large coefficient of thermal expansion, low freezing point and high boiling point, and the temperature thermal expansion of liquid should have a linear relationship between the temperature and the desired range of measurement. Okay, so it's quite understandable from the statement itself, but let us just go through them once so that it becomes a bit more clear. Okay, so first is the large coefficient of thermal expansion. Okay, so the thing is, like for example, if you're using a thermometer where the fluid the difference in the fluid expansion is quite low between two different temperature range, or two different temperature values, then it will become quite difficult to read between the scales. Okay, so for example, if there is if the liquid in the thermometer rise up to a value of only 1 millimeter, say, for a temperature change of say 10 degrees Celsius, then it becomes quite difficult to measure temperature values which have temperature variations say of 5 degrees Celsius. So it will vary to 0.05 to 0.5 millimeter, which is almost imperceivable by a human eye. Okay, so that's why it's desired that it should have a large value of thermal expansion coefficient, so that even for small temperature changes, the liquid inside the thermometer should vary a certain value, so that the reading between the temperature values becomes easier. Second is low freezing point and high boiling point. Okay, so you can see that the requirement is that the fluid inside the thermometer should be in the liquid state. Okay, so it becomes quite desirable that, since if it has a very low freezing point and a very high boiling point, so the range of temperature in which the thermometer would work becomes larger. Okay, that's why it's I would say it's what to say, it's beneficial if the value of the freezing point is low and the value of the boiling point is high for this kind of liquids which are used inside the thermometer. Okay. Finally, the thing is, the thermal expansion of liquid should have linear relationship with temperature and the desired range of measurement. Okay, so this is something that we have already solved. We saw that we mentioned in the while discussing about these thermometers or the first the zero law of thermodynamics that it is ideal if there is a linear relationship between the temperature variation and the rise of the liquid column inside the thermometers. Okay, say if the relationship becomes say quadratic or cubic, again this becomes quite difficult to calibrate. There is finding the value of your constants in the relations, and it becomes quite difficult to observe as well. Say for example, if the temperature, if in the lower temperature spectrum the liquid varies linearly, for example say for 10 degrees Celsius it shows 1 millimeter deflection, and for 20 degrees Celsius it shows 20 millimeter deflection. Okay, sorry, 2 millimeter deflection. It's a linear relationship. But say in the higher end of the spectrum, say around 80 or 100 degrees Celsius, the relationship becomes different. For example, for 10 degree difference it is showing your say 1 millimeter deflection, but for 20 degree difference it is showing 40 millimeter deflection. So the relation becomes non-linear and it's not desirable. Okay, so that's why it's desirable that if the relation becomes is linear throughout the range of operation, then first thing is that the calibration becomes easier. Second thing is that the measurement of the temperature becomes convenient. Okay, so that's the two things. Now let's go to question number 3. Okay, I hope it was understandable. Let us go to question number 3. Okay, thermometers A and B are calibrated at the ice and steam points. Again these are very crucial statements that they are calibrated. Okay, thermometers, both thermometers A and B are calibrated at the ice and steam points. Okay, the relationship between the temperature measured by A and B is given by, oh sorry, I think we already did this example, so we can skip that part. Okay, yeah, let us look into this question. This question. A stationary mass of gas is compressed without friction from an initial state of 0.3 meter cube and 0.105 megapascal to a final state of 0.15 meter cube and 0.105 megapascal. So pressure, you can see, is remaining constant. Okay, that's one thing to observe. Pressure remaining constant during the process. There is a heat transfer of 37.6 kilojoule from the gas during the process. Heat transfer from the gas during the process. How much does the internal energy of the gas change? Okay, so I think again it's a very simple implementation of the first law of thermodynamics. You need to find the work done from these relations. Okay, from these relations, these values. The net heat interaction is already given. Find the net change in the internal energy. Okay, or delta U, I must say. So I will give you 4 minutes again to try to solve this question, and then we can proceed further. Okay, very simple, not that difficult. Simply just find the work done, the constant pressure work done. Okay, isobaric process. Substitute these values in the first law of thermodynamics. Now then tell me the net change in internal energy. Okay, 2 more minutes, then we can discuss it. Okay. Okay, 37.61 kilojoules. Okay, so yeah, okay. Oh, there's okay. Let's look into it. That's the case. Okay. So yeah, this is the thing. So from the first law of thermodynamics, you will have Q is equal to delta U plus W. Q1 to 2 would be U2 minus C1 plus W1 to 2. Now W1 to 2, he saw that the pressure was constant, and it was mentioned that the pressure remained constant throughout the work done. Then we have work done from 1 to 2 is integration of 1 to 2. Okay, thank you. Work done from 1 to 2 PdV. Okay, where P is constant, so it becomes P V2 minus V1. Work done becomes 0.105 minus times 0.15 minus 0.3 or minus 15.75 kilojoules. Okay, so work done is 15.75 kilojoules. Okay. Because it's 0.105 megapascal, right? So if you convert it to kilopascal, then becomes 105 kilopascal. Okay, so kilopascal times your change in volume will give you energy in terms of kilojoules. Okay, then work done from 1 to 2 is minus 37.6 because heat is transferred out of the system. Okay, so we will have minus 37.6 is equal to U2 minus E1 minus 15.75. Okay, yeah. So if you do that, yeah, thanks, as work is done. Yeah, thanks, Jitendra. So if you do that, you'll see that U2 minus E1 becomes minus 21.85 kilojoule or 21.9 as mentioned by Jitendra. Okay, so is it clear, Astha and Jay? Yeah, thanks, Jay. Astha, is it clear? Okay. Okay then. So let us look into the next question. Yeah, this question is a bit lengthy one, so I think I'll keep it for the last. Okay, so let us look into this question first. Again, I will give you this one as well for your exercise. Let us see whether you understood it properly or not. Okay. A stationary fluid system goes through a cycle. Okay, goes through a cycle. These are important terms to remember. Okay, goes through a cycle, as shown in the figure given below, comprising of the following processes. Okay, process 1 to 2 is an isochoric heat addition of 235 kilojoule per kg. Okay, also look in the units of heat. So it is saying heat energy per unit mass. Okay, that's fine, but look into the units as well. 235 kilojoule per kg. Process 2 to 3 is an adiabatic expansion to its original pressure. Okay, to its original pressure with a loss of 76 kilojoule per kg of internal energy. Okay, so the net change in internal energy from process 2 to 3 is minus 70. Okay, internal energy reduces, so minus 70 kilojoule per kg. For process 3 to 1 is an isobaric compression to its original volume. Okay, so it goes back to its initial volume with heat rejection, again heat rejection of 200 kilojoule per kg. Okay, so with these informations, prepare a balance sheet. Okay, this one you can just leave for the last. Okay, leave for the last. But right now, what you should do is you find for me. Find me the total heat interactions. Okay, the question would be find the summation of Q and the summation of W for the cycle. and hence show that summation of Q is equal to summation of W for a thermodynamic cycle. So since we have limited time, I will not ask you to create a table or anything. Okay. But more or less you are doing that same task. You are finding all the work and energy interactions, work and heat interactions for all these different cycles. Just show that first, okay, you can find either of them just for the ease of your understanding. But the thing is, again, you need to find all of them to find the total heat interaction or total work interaction. Okay, so more or less you do the complete exercise. So either you tell me the total work interaction or total heat interaction. I think then the exercise will be done. Okay, so I hope the question is understood. Diagram is given. Just put in whatever values are given in the question, substitute it in your diagram in the first law of thermodynamics, then tell me the solution. Okay, it's not that difficult. Okay, see, for example, in the isochloric heat addition, the PdV work would be 0, so heat addition should be equal to your change in internal energy. First thing done. Okay, similarly go to the next step. Okay, all the key terms are already given in the question. No need to no need of any additional information. Just try to solve them one by one and then tell me either summation of Q or summation of W for this thermodynamic cycle. Okay, what's the value? So it's 7:32. I will give you say 7:30 up to 7:37 time. Then we will discuss the solution. Okay. Meanwhile, if you have any doubt, you can ask. Try to solve. Okay, I need some response before 7:37. Okay, so 3 to 1. Okay, let me just check. Okay, yeah, that's correct, Jay. That's correct. Yes, 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 it's correct. Okay, so Jay has already given his answer. So others, Astha and Jitendra, can also contribute. Say 2 more minutes. Yes, yes, Jitendra, that's correct. Yes, yes, Asta, that's also correct. 2 to 3, no, 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 no. 2 to 3 would have a work done because there is an expansion going on. 1 to 2 does not have a work done, okay? Because it's an isochoric process. Constant volume process would not have uh, any PDE work done. So from 1 to 2, work done is 0. 2 to 3, there is a work interaction. Then you need to find out the pressure, internal energy is, change in internal energy is given, heat interaction is 0, so you can easily find out the work done, right, from the first law of thermodynamics. Internal energy decreases, okay, so you need to be aware of the sign convention. Okay, one more minute. Nevertheless, thanks for trying. One more minute, you can try it out, then we will see the solution, okay. Okay, time's up it seems. So let us, thanks again to all of you for trying and answering. Let's look into the solution. It's quite simple, but again it's important to know, okay. So this is the diagram. So heat interaction from 1 to 2 is given as 225 kilojoule per kg. Work done from 1 to 2 is 0 because an isochoric process, okay, constant volume process. So work done from 1 to 2 is 0. So from the first law of thermodynamics, the net change in internal energy from process 1 to 2 is 235 kilojoule per kg, okay, because this is 0 and q 1 to 2 is 235, so net change in internal energy is 235 kilojoule per kg. Again, intuitively also you can understand that if heat is added to the system, the vibrations of the molecules of the system will increase, which will in turn increase the internal energy of the system, given that it's not doing no work, so energy will be stored within the system, okay. Second is an adiabatic expansion. So since an adiabatic process, so the net heat interaction is equal to 0, okay, q will be equal to 0, right. So from the first law we'll have that work done, negative of work done from 2 to 3 is equal to u3 minus u2, okay. Since the change in internal energy is given the question is decreased from to decreased by 70 kilojoule, so we will have that minus work done of 2 to 3 is equal to negative of 70 kilojoule. So cutting all negative side from both the sides, we will get work done from 2 to 3 as 70 kilojoule per kg, okay. Then from process 1 to 3, the net work interaction, the net heat interaction is minus 200 kilojoule per kg. Heat is again lost by the system, so heat interaction is minus 200 kilojoule per kg, okay. Now the net change in internal energy from process 3 to 1 can be just one second, can be found out using this simple manipulation, okay. So u1 minus u3 can be written as negative of u3 minus u2 minus u2 minus u1, okay, because see, you already know u3 minus u2 and u1 minus u2 because all these values are already known. That's why using these values you can easily find the value of u3 minus u1, okay. So if you manipulate this arrangement and do that, you get that. Since so see, let us just show you how they are equal, okay. So if it becomes, this summation becomes minus u3 plus u2 negative negative positive minus u2 negative negative plus u1, so it gives you u1 minus u3, right. So negative of u3 minus u2 minus u2 was minus 70, so minus of minus 70 is plus 70 minus U2 minus U1 was positive 235, so minus 235, so it becomes minus 165 kilojoule per kg. So if you substitute this in the first law of thermodynamics for process 3 to 1, you will get that work done from 1 to 3. 1 to 3 is Q1 to 3 minus U1 minus U3. So if you substitute the values of Q and work and then change the internal energy, you will get that work done from 1 to 3 is minus 35 kilojoule per kg. Okay. So if you sum now all the work interactions, work done from 1 to 2 is 0. So the only work interactions are 2 to 3, 2 to 3 and 3 to 1. Okay. Then 3 to 1. So if we add them up here, so you will get that net work done by the cycle is 35 kilojoule per kg, which should ideally be equal to the net heat interaction in a cyclic process. Even though if you do it, see, the net heat interaction is heat added to the system in process 1 to 2, so it is plus 225. It's adiabatic, so heat interaction is 0, Q equal to 0. Again, heat is rejected from process 3 to 1. So if you add all of them up, you will get that the work done by the net heat interaction in a cycle is 225 minus 200, or which is equal to 35 kilojoule per kg. Okay. So I hope this is clear. Astha, is it clear? I don't know whether they are here or not. Okay, so Astha is there still. Okay. Thank you. Yes, thanks Jay. Thanks Jitendra as well. So let us try to solve one more question. I think we have enough time. Okay. So let us go to this question. Okay. This will be a bit lengthy. Not that much, but it will be a bit lengthy compared to the problems that solved till now. Let us look into it. Okay. When a system is taken from state A to state B, okay, state A to state B, figure given below, along the path ACB, 84 kilojoule of heat flows into the system. Okay, I think I should underline them for your ease. Path ACB, 84 kilojoule of heat flows into the system, and the system does a work of 32 kilojoule. Okay. Question A is, how much heat that flows into the system along the path ADBB if the work done is 10.5 kilojoule? Okay. That's the first question. When the system is returned from B to A along a curved path, okay, along a curved path, the work done on the system is 21 kilojoule. Okay, the work done on the system is 21 kilojoule. Does the system absorb or liberate heat? Absorb or liberate heat? That's the first question. On how much of the heat is absorbed or liberated? Okay, you need to find the value of this heat interaction as well. So final question is, if UA is equal to 0 and UD at point D is equal to 42 kilojoule, find the heat absorbed in the process AD and AB. Okay, so this may seem quite a lot in the beginning. So for the ease of that, I would ask you to solve the problem one by one or step by step. Okay, first is your part ACB. Okay, first is your part ACB. First, try to solve the problem along this path. Okay, all the work and energy interaction are given. You can then find the internal energy. Similarly, then solve for part ADB as mentioned in question A. You need to know how you can use the concept of internal energy being point functions in this particular question. Okay, then similarly solve for other problems. Okay, then I think for now let's try to solve this problem in parts. I will give you say 4 minutes for part A. Okay, question is, how much of heat that flows into the system, how much will be the heat that flows into the system along part ADBB if the work done is 10.5 kilojoule. Okay, so tell me the answer of part A, say by 7:49. Okay, I think that's doable, so let us do that and then we can discuss if required. Okay. For question A, Jay is saying that the net heat interaction would be 62.5. Okay, let me just see. Okay, so Jay, that's correct. Others, Jitendra and Astha also, you can try. Let us see whether you can get the same answer or not. So Jay, I think now if that's the case, then you can proceed to B. Okay, Astha and Jitendra also, if you get the answer, yeah, Jitendra also, yes, thanks Jitendra. Then you can also now proceed to B. Okay, so Jay says the proceed is B is 73 kilojoule. Okay, so question B was, oh, Astha also, yes, Astha, thanks. Part A is correct. So now I think all of us can go to question part B, and Jay is saying is 73 kilojoules. Okay, so the question was, when the system is returned from part B to A along a curved path, the work done on the system is 21 kilojoule. Does the system absorb or liberate heat? Liberate, then I think it should be a negative sign, right, Jay? Yes, right? It should be a negative sign, liberates heat, right? Then it should be minus 73 kilojoule. Okay. Yeah, no, it's fine, it's completely fine. Okay. So Jitendra and Astha also, just look into it. If you get it, then I think Jay can proceed to C. Astha and Jitendra, just try out B whether you get similar answer, and then you can proceed to C as well. Okay. Yeah, thanks Jitendra. Astha also, you can try. Yes, thanks Astha. So if that's the case, then all of you can just proceed to the final part. This, if UA is equal to 0 and UD is equal to 42 kilojoule, find the heat absorbed during the processes AD and AB. Okay. Okay, so QAD is 53.5 as mentioned by Jitendra. Let me just check. QAD is 53. Let me just check. You can just say whether it's 53 or 52. Yes, 52. Yeah, correct. Then you can tell me for QDB as well. QDB. (73). QDB 73. Let me just check. Okay, QDB, I think you need to check again. Okay. What will be the value of UB? AB is, yeah, exactly. You need to know what should be the value of UB, then UD, then WDB. What will be the value of that? So I think I will wait for 1 more minute. Just see whether that's worked or not. Okay. Uh, 52. So let us. Yes, yes, yes. Okay. So let us try to look into the solution. Okay. Thanks a lot again for trying. Okay. Just yes. Okay. So let us see. Okay. So the first part was QACB is 84 kilojoule and QWACB is, since you have already have solved the questions, I don't think I will need to go through the steps thoroughly, but for other viewers who will just see the session for the solution part, I think it will be good to show them solution as well. Just let me know if any step is wrong from my end. Okay. So QACB is 84 as given in the question and WACB is 32. So from that you can get that QACB, from first law, QACB is equal to UB minus UA plus WACB, or UB minus UA is 84 minus 32 or 52 kilojoules. Okay. So the first question is find the net what's the heat interaction along this path. Okay, along path ADB. Okay. So the net work interaction is given, that is 10.5. You need to remember that since an internal energy is an point function, so it is independent of path. So the net change in the internal energy, whether going from this path or this path, would be the same. Okay. So for QADB is equal to UB minus UA plus WADB, or QADB is equal to 52, which is same as this one, plus 10.5, that is the work done as given in the question. So it gives us QADB is 62.5 kilojoule. Okay. Now for part B, if I go into the question, let me just go through it. Part B, the question was, when the system is returned to from B to A along a curve, but the work done on the system is 21 kilojoule. Does the system absorb or liberate it? Okay, so we need to solve the question along this path. Okay, along this curved path. So we have QB to A is equal to UA minus UB plus WBA, because UA is the final point. We are going from B to A. Okay. So UAB is again just the opposite of this one. Then we have minus 52 plus WB to A, because again work is done on the system. So QBA would be minus 73 kilojoule, which means that the system is liberating heat or releasing heat, rejecting heat. Okay. Now for the final part, it is given that if UA is equal to 0 and UD is equal to 52, UD is equal to 42 kilojoule, we know that UB minus UA is 52 kilojoules. Okay, so from that we get that UB is 52 kilojoule because UA is equal to 0, and WADB is equal to 10.5 kilojoule. Okay, as mentioned in the question. Okay, WADB is 10.5 kilojoules. Now from in WADB, it is WAD plus WDB. Okay, now WDB would be equal to 0 because net change in the volume is equal to 0. So PDB work is equal to 0. So WADB would be equal to WAD is equal to 10.5 kilojoules. Okay, now QAD is equal to UD minus DA plus WAD. So UD minus DA would be 42 as mentioned in the question, because UD is 42 and UA is 0, and WAD would be 10.5 as obtained from this. So we will get QAD as 52.5 kilojoule. Okay. Finally, for QDB, we will have UB minus UD plus WDB. UB is 52, UD is 42 as given here. So we will have, and WDB is equal to 0 because the net change in the volume is 0. So QDB is UB minus UD, or 52 minus 42 as, or equal to 10 kilojoules. Okay. So is it fine? Is it understood? Okay, thanks Astha. Jai Jitendra. Thanks Jitendra. Okay. So I think we have time for the last question. I think last question. Let us just look into it. If you have any doubt, you can ask, or I think it's quite easily solvable. Okay. An engineer has proposed a new temperature scale in which the ice point of water is taken to be 200 degree Q and the steam point is taken to be 500 degree Q. Okay, so this is a new temperature scale proposed by the engineer. So ice point is 200 degree Q and the steam point is 500 degree Q. What are the corresponding values of degrees Celsius for 100 degree Q and 300 degree Q? The relationship between two temperature scales are assumed to be linear. Okay, so yeah, so I think it's quite simple again. You need to find a relationship between the Celsius scales and the degree Q scale and tell me the value of, say, for today first we can just do this part. What will be the value of the degree Celsius for 100 degree Q? Okay, so I'll just give you a hint. uh, I think since we are out of time, let us just go through the solution from our end. Okay, then you can just try it out. I will just show you for the T equal to 100 degrees Celsius, then you can accordingly do for T equal to 300 degree Q. Okay, so let's look into it. Okay, yeah, so the given that let T dash ice be the temperature scale for the new units of temperature. Okay, so T dash ice is 200 degree Q and T dash steam is 500 degree Q as given in the question. But we know that for our general case, T ice is 0 degree Celsius and T steam is 100 degree Celsius. Okay, so it is given that the relationship between the two temperature scales are linear. So we can say that T is equal to ABT dash or T dash equal to ABT according to your requirement. Okay, and if you change the relationship, then the values of the constants will also change. Okay, so we have that the steam point for the new temperature scale is 200. Okay, not steam point, sorry, the melting point. Okay, ice point, but ice point for our degree Celsius scale is 0 degree Celsius. Okay, so we have 0 is equal to A plus B times 200, and similarly for our degree Celsius scale, the boiling point is 100 degree Celsius, which is equal to A plus B times 500, where 500 degree Q is your new temperature scale. So if you solve these two equations, you will get that B is equal to 1 by 3. Okay, and A is equal to minus 200 by 3. So the question was to find the value of the degree Celsius value for T equal to 100 degree Q. So for T dash equal to 100 degree Q, just substitute the value of 100 degree Q in this relation and substitute the value of A and B. So from that we get that A is minus 200 by 3 plus B is 1 by 3 times 100 is 100 by 3, or T is equal to minus 100 by 3 or 23.33 degrees Celsius. Okay. So I hope it's done. Similarly, you can find the value of 300 degree Q as well. I think I can leave that you as an exercise. So I hope this was clear. Okay. Thanks, Astha, Jitendra, and Jay. So I hope this session was useful. Yeah. Okay. Okay then. So let us all of us meet in the next session. Okay, next week. Thank you.